Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 4, and this problem asks us to draw a stepwise mechanism for the sulfonation of this alkyl benzene from the conversion of A to B. So what we're doing here is what we call electrophilic aromatic substitution, EAS. So in electrophilic aromatic substitution, there's two steps or two parts to this mechanism. Number one is that you need to first create your electrophile. So you need to make some sort of very electron poor or positively charged molecule in which your nucleophile, being the benzene ring, can then nucleophilically attack. The second part is going to be the substitution reaction, in which you're actually going to add on your electrophile to your benzene ring with a loss of a proton on that benzene ring to reform your acid catalyst. So let's draw the part one. So we need to form our electrophile. So the reagents we have is SO3, so let's draw that. And we have hydrochloric acid. So we can draw that something that looks like this. So we need to form our electrophile, and our electrophilic species is going to be this moiety here, this molecule here. So what we know is that we can use one of the pi bond electrons of our oxygen sulfur bonds to pick up this proton to protonate this oxygen, making a bond. You make a bond, you break a bond. And we know that as hydrochloric acid is more than willing to donate its proton to this molecule since of the very low pKa of HCl. So now we form a protonated sulfonium ion plus our conjugate base, HSO4 minus. So this group actually equals this group. So this is equal to saying SO3H, the positive charge on sulfur. So we can actually draw that positive charge on sulfur. Now we formed our electrophile. So this is now our electrophile here. So now what we can use is now we can go to part two of this electrophilic aromatic substitution reaction, use our alkyl substituted benzene ring, and I'm going to make kind of a let statement. I'm going to say, let this hydrocarbon chain equal R. So I'm just going to say we have an R group here, which is this hydrocarbon chain. And we know that each of these carbons have protons. And not only we know that this electron donating alkyl group, it donates or activates the ortho and para position for electrophilic aromatic substitution. So we know that we're going to get some sort of isomeric mixture of ortho-substituted and para-substituted products. However, here we're only interested in the para-substituted, so we're just going to focus on that. So we know that now our benzene ring is going to be, the source of our electrons is going to be our nucleophile, and we know that we're going to use the two electrons in one of these pi bonds to go through this carbon that's at the para position and attack our newly formed electrophile, making a bond. The formation of this bond actually neutralizes the sulfur group of our electrophile. So now we just get an SO3H, and we have those two pi bonds still remaining here, and the R group is still here. But now we've actually lost a bond at this carbon right here. So now here we only have 3 bonds, so we have a carbocation intermediate. So now, remember, this reaction is acid catalyzed. So in any sort of catalyzed reaction, you always must reform your catalyst. So we can go ahead and reform this catalyst, but let's just show some sort of resonance stabilization of this carbocation intermediate before we do that. So we can move around the pi bonds of this molecule to show the resonance stabilized intermediate. And this will kind of help us understand why electron donating groups are ortho and para activating. And we see that now the carbocation intermediate is placed on a carbon that's attached to our hydrocarbon chain here, R group. So because this carbocation positive charge is now on this carbon, which is attached to our hydrocarbon, we have some sort of inductive stabilization of this carbocation intermediate. Therefore, it stabilizes and lowers the actual energy of this transition state, or this intermediate group, sorry, and therefore this is a favorable reaction. This is why donating groups are ortho and para donating and activating. And this is why they're not meta-directing, because you don't get any sort of stabilization from meta-substituted carbons. So now we drew all the resonance structures of how our carbocation can move around our benzene ring. And we have our conjugate base, and we know that we need to reform our acid catalyst, and we know that this position here is where this carbon here originally had this hydrogen right there. And we know this hydrogen is still present throughout this entire process. So what we can do is we can use the lone pair electrons on our oxygen to pick up this proton. So this does two things. Well, now you reform your aromatic compound. So you made a bond with the oxygen and hydrogen, so you need to break the bond, the sigma bond here. Now you made the pi bond. Now you're just going to move these alkene bonds around. So now you reformed aromaticity in your benzene ring, but number two, you now neutralize this carbocation intermediate. And in the process of that, not only do you reform your benzene ring, but you also reform your acid catalyst.